In this lesson, we cover the I2C theory of operation. You can see the topics here, which I'll go through quickly. We start with an introduction, which includes advantages and disadvantages of I2C compared to other serial buses. Next, we'll cover terminology and some of the basic concepts of I2C. Then we'll look at how open drain signals work. And this is a hardware concept, but it's not too hard to understand. We'll look at a circuit that shows how I2C devices are connected to an MCU. And following that, we'll look at the details step by step of how the I2C bus operates. Next, we'll look at some other I2C features and procedures. These are less commonly used, but it's good to be aware of them. Finally, after a very short summary, I'll provide some prompts or questions for you to try to answer. For each prompt, I'll give you a second to pause the video if you'd like, and then give you my take on the prompt. Now down here in this box is a reference to the I2C specification. As specs go, I find this one fairly easy to read, and I encourage you to take a look at it. You might notice that NXP writes the spec, and of course they make a lot of chips, including MCUs. Let's start with an introduction to I2C. So I2C stands for Inter-Integrated Circuit and is pronounced either I2C or I2C. It's one of several serial communication methods you'll see in embedded systems. I2C is commonly used for an MCU to communicate with external sensors, external memory, I/O extenders, displays, and other devices. Other serial communication methods are asynchronous serial, which uses a UART, SPI, and CAN. These different interfaces tend to have different intended uses, and with that, different advantages and disadvantages. For example, I2C and SPI tend to be local to a board or a closely connected set of boards, so the bus would normally be no longer than a meter. Of course, there are exceptions. In contrast, CAN and some types of asynchronous serial can be used for 100 meters or more. So in looking at I2C advantages and disadvantages, we will mainly be comparing it to SPI and asynchronous serial. And by the way, you can Google I2C versus SPI and get lots of information on this subject. So let's start with some advantages of I2C. This first one might be the biggest. You can communicate with multiple devices with just 2 signals besides ground. With SPI, you need more signals, often including one dedicated signal for each device. Another advantage is there is some built-in error detection. As we shall see, ACK signals are used to give a positive confirmation of correct operation. With SPI, there are some error conditions that can go undetected. And compared to asynchronous serial, I2C does message framing. In other words, you don't have to write code that determines the starting and ending points of a message. So now for some disadvantages of I2C. This first one, speed, is probably the biggest disadvantage. The main reason for this slower speed is the use of open drain bus signals. This is an electrical issue. Using open drain helps to reduce the number of signals needed by allowing them to be shared between devices, but it slows things down. Because of open drain, you often need pull-up resistors with I2C. It isn't a big deal, but it is a minor cost and it takes up a little board space. And the final disadvantage I list is possible address conflicts. It is hard to say how often this is a problem, but it does happen. And I'll wait until we talk more about I2C addressing before explaining this. So now that we have found out how I2C is used and what its advantages and disadvantages are, let's start learning about some terminology and concepts. So first, let me just define a term. A transaction is the transfer of information on the I2C bus between devices. It can consist of one or more read and write operations. As we shall see, there are distinct markers at the start and end of a transaction. Now let's talk about addresses. Because multiple I2C devices can be connected to the same bus, there must be a way for devices to identify each other. This is done via an address. Each device on a bus must have its own unique address. The way this works is that the first byte written to the bus in an I2C transaction contains the address of the target device. So the selected target device will participate and all of the other devices on the bus will stay silent. Now, addresses are normally 7 bits in length. We will talk about 10-bit addresses later. The next concept is master and slave. For a particular transaction, there is a master that initiates the transaction and a slave that reacts to it. So at the start of a transaction, the master sends an address to select a particular slave on the bus. It's most common that an MCU is the master and some external device like a sensor is the slave. However, an MCU can act as a slave for some applications. Now, it's most common that there is a single master on the bus. A bus with multiple masters is possible, but we will focus on the single master case in this course. One last thing I want to mention is that in an I2C transaction, the master has no address. It doesn't need one. Now let's talk about open drain electrical signals. And I need to mention there is something very similar called open collector, and you can view them as the same. And open drain is just an electrical technique to share a signal between devices. So here we have a signal, and I just call it an I2C bus signal. Now with I2C there are actually 2 open drain signals, but I show one here just to keep it simple. And as you can see, there are 3 I2C devices connected to this open drain signal: an MCU, a sensor, and an A to D converter. And I show that each device is connected to ground, which is 0 volts. Often ground connections are not shown on schematics and are just assumed, but on this first slide I include it. And as seen here, ground is sometimes called VSS or labeled VSS, where S means source, or VEE where E means emitter. Now there are technical reasons why they use all of these names, which you don't really need to worry about. So the bus signal is at the high level by default due to this pull-up resistor. In other words, this resistor pulls up the signal to the high level. Now this high level is in reality a high voltage level, normally either 3.3 or 5 volts, but we can just call it a high level. And as seen here, it is sometimes, this high level is sometimes labeled VDD for drain or VCC for collector. So devices, any of these 3, just leave the signal alone if they want it to be high, because the pull-up resistor is pulling it high. But they pull it down to make it low. When any of these devices pulls the signal low, it overpowers this pull-up resistor. As soon as the device leaves it alone, the pull-up resistor will pull it back high again. Now I show this concept in a little more detail in this yellow box, which contains the bus interface for these I2C devices in a very simplified way. First, it shows that the device can always read the level of the signal. And it shows that the device can control the signal through this conceptual switch. When the switch is open, as it is here, it has no influence over the signal level. But if it closes the switch, connects this, that will connect the signal to ground and make it low. So the switch overpowers the pull-up resistor. So these devices can control the level of the signal and can also read the level of the signal. And this is how data is transferred. One device is controlling the signal and another device is reading it. Now, of course, for this to work, it has to be very organized, and the I2C protocol specification does this. It provides the rules for how data transfer works. It specifies in great detail a series of steps for some operation, like a read, and for each step, how the different devices control or read the I2C signals. We'll look at this shortly. Here we show an example of an I2C circuit. Let's imagine this is a controller for a refrigerator. We have an MCU and 4 other I2C devices, 3 temperature sensors and an A to D converter. You'll notice that there are 2 I2C buses on this board, and we'll talk about the reason why in just a minute. Each bus has 2 signals, and these signals are open drain, as we just discussed, and they have pull-up resistors. One thing I did on this drawing is show 2 styles for drawing resistors on a schematic. The traditional style is this zigzag style, which I like, but you will also see these rectangular style. And of course, no one would mix styles on a single drawing, which is what I did here. So again, we see that the I2C bus has 2 signals, SDA and SCL. And SDA is used to transmit and receive data, serial data, that's the SDA. And the other signal is the serial clock, and that's where the SCL comes from. We will see later how these signals work. As I mentioned, the I2C master is typically the MCU, and there is only one, and that's what I show here. And I2C slaves are typically sensors, A to D converters, memory I/O expanders, and so forth. And this is what I show here also. We talked about I2C addresses and that each slave on a particular I2C bus must have a unique address. Now, this note here says that the temperature sensor can only be configured to have addresses hex 44 or address hex 45. And this is exactly the case with the temperature sensor I use in this course. It is limited to these 2 addresses, and that kind of address limitation is common in I2C devices. So if we need 3 temperature sensors, and if we had just a single I2C bus, we'd have a problem. We have 3 devices, but only 2 unique addresses. Now, there are different solutions to this problem, and they all involve hardware design in some way. This drawing shows one particular solution, and that is you just add a second I2C bus. So now we have 2 sensors with address 45, this one and this one, but they're on different buses, so it works fine. This is a simple and fairly cheap solution if you have a spare I2C bus on your MCU. And that's not unusual. The MCU we are using in this course has 3 I2C bus interfaces, so this would work. Now let's talk about I2C bus operations. They occur as a series of steps, as I'll describe here. I'll first start with this very abstract diagram to focus on the steps before we start looking at the details of the SDA and SCL signals. So first, your software running on the MCU acquires the bus. Both the SDA and SCL signals must be high, which indicate the bus is idle. If you have a single master, this should always be the case. However, I would not rule out the case that if you start a new transaction immediately after a previous one ended, or after some bus error, you might have to wait a short time and retry. Next, the master generates the start condition on the bus. This tells all slaves to wake up and start listening. This is the start of the I2C transaction. Next, the master sends the slave I2C address followed by a read-write bit that tells the slave whether the master wants to read data or write data. So all the slaves compare this address that the master sent with their own address. If there's an address match, then the slave sends an ACK, and all the other slaves stay silent. But what if the address did not match any slave? Well, no one would send an ACK, and the absence of an ACK is considered a NACK, N-A-C-K. NACK stands for not acknowledge. So if the master detects a knack, it will stop the transaction there because there's no one to talk to. And we'll look at this case in one of the demos. But assuming an ACK was sent by a slave, we are now ready for the data transfer. So there is the write case and the read case. I show them both here, but only one will occur. And the way they work is similar. In each case, the sender, which would either be the master or the slave, transmits a data byte, and the receiver sends an ACK. And this process repeats for each byte. And these arrows here are meant to indicate this is a loop. Now, the way the data transfer ends is different between reads and writes. For a write, normally the master simply stops sending when it has sent all the bytes at once. It is not common, but possible, though, for the slave to terminate the transfer before that by not ACKing a byte. Again, the absence of an ACK is viewed as a knack. For a read, it is normal for the slave to send bytes until the master has what it wants. The master knacks the last byte at once, and the slave knows that data transfer has ended. So in both the read and the write cases, the master generally controls how many bytes are transferred. And then finally, the master generates the stop condition. This indicates to all devices that the transaction is over and the bus is idle. Now, one thing I should say is that the I2C specification, for the most part, says nothing about the meaning of what these data bytes contain. That is all up to the individual I2C devices, such as sensors or memory. So now I'm going to repeat what we saw in the last slide, but this time in terms of the SDA and SCL signals. For those of you who have not seen signal diagrams like this before, I'm going to spend a little time up front explaining them. So here are the two signals, SDA and SCL. And these traces are showing the state of those signals, high or low, as we go forward in time from left to right. In terms of data, a low signal indicates a 0 bit and a high signal indicates a 1 bit. In terms of ACKs and NACKs, a low value indicates a ACK and a high value indicates a NACK. Now you'll notice areas where the SDA signal is both high and low at the same time. Now what that means is we don't know the value of the signal. And so in this case it's the address being sent. We don't know what the address would be, so it's going to be zeros and ones through here. On the other hand, in the case here where the ACK is being sent, we know that it's an ACK and it's not a NACK. And so that's why it's low here. How do we know it has to be an ACK? It's because if it was an ACK, the transaction would be ending. We wouldn't continue on with data transfer. So the SDA signal has bit values and ACK-NACK values, and it goes high and low to convey this information. The question is, if you were trying to receive these bits, you would say, well, where does a particular bit start and end? And this is where the clock signal comes in. And it's fairly simple for I2C. Whenever a clock signal goes from low to high, you should look at the value of the SDA. And that will tell you whether it's a low or a high. So a hardware designer would say that we sample the data signal on the rising edge of the clock signal. And after the falling edge of the clock signal, for example here, that is when it is time to change the SDA signal to be ready for the next bit. And that's what it's showing right here. The SDA signal may change at that point. So this here indicates, as 1 to 7, indicates that there will be 7 rising edges of the clock signal for the 7 bits of the address, and the values of those bits will be up here, and again we sample them when the clock rises. And then this rising edge here indicates when to look for the read-write bit, and this rising edge here indicates when to look for the ACK-NAC signal. One important thing I want to say about ACK-NAC, for the address and read-write bits, the master was controlling SDA, but the slave sends the ACK-NAC. So right after the read-write bit, the master lets go of the SDA signal, and that allows the slave to control it. And this is where the idea of open drain comes into play. However, I should mention that even though in this case the slave is controlling the SDA, the master always controls the clock signal. And I should say almost always controls the clock signal. There is an exception I'll talk about in a little bit. So once you get the idea of the clock signal and how it tells you when to sample the data signal, you have learned a key concept in digital sequential logic. So transmitting data bytes works the same way as the address and read-write bit. Depending on whether it's a read or a write, either the master or the slave will be putting its bits on the SDA signal. And whether it's a read or a write will determine whether the master or the slave is the one sending the ACK signal here. So this is how the bus works. Once you get the idea, it isn't hard. And we'll be looking at more of these diagrams on a logic analyzer in a following lesson. Now the final thing I need to mention are the start and stop conditions. For instance here. These are special unique bus signal patterns. The uniqueness is based on the fact that when data is being transmitted, the SDA signal does not change while the SCL signal, the clock, is high. If that does happen, it's a start or a stop. So a start condition is when there is a falling edge on SDA while the clock is high. And a stop condition is when there's a rising edge on SDA while the clock is high. So that's it for the bus operation at the SDA and SCL level. So we've seen the basic operation of the I2C bus. Over the next few slides, I want to discuss a number of I2C features and procedures that I didn't really explain yet. Some of these are not commonly used, but it is good to be aware of them. Unfortunately, I'm not covering everything. There is even more. If you want to learn about these other things, I suggest you take a look at the I2C specification. It's not that hard to read, and at this point a lot of it should look familiar. So I've referred to multi-master before, and the main thing it adds is bus arbitration. So when a master wants to use the bus, it first has to check if it's busy. And if it is busy, it means there's another master using it and it needs to back off and try again later. So that handles most of the arbitration. The tricky case, though, is when both masters try to use the bus at exactly the same time. They both see the bus as non-busy, and they both start to use it. This is known as a collision. Now there is a hardware method for the two masters to detect that a collision is occurring and for exactly one of the masters to back off. The other master will keep going and the operation should work. So now bus speeds. The bus speed is how many bits can be sent per second, and it's more or less the same as the clock frequency. The bus speed is stated in terms of mode. So the original I2C spec was standard mode. It allows you to go up to 100 kilobits per second. Things always have to go faster, so they came up with fast mode, which is up to 400 kilobits per second. And then, there's even faster modes. The bulk of I2C buses probably operate at one of these two modes, although these faster modes were put in there for a reason. So clock stretching is a cool little feature. Suppose the master is trying to write data to a slave, and say the slave needs a little extra time to process the data after each byte, for example. The slave can pull down the SCL signal to low to indicate it needs some time. And again, it's open drain that allows this kind of thing to happen. So the master will detect this, and it will wait until that SCL signal goes high again, and then it can continue operation. Now, the master might also want to slow things down for some reason. It's a little bit easier for it since it controls the clock. It can just stop the clock, and as long as it needs to, and then start the clock again when it's ready. And the slaves probably won't even notice this. So your software really doesn't have to do much. There is sometimes an option to allow or disallow clock stretching, but for the most part, this is just a hardware feature. Continuing on, we have what is known as combined format. This is a way to do two or more operations in a single bus transaction. Most commonly, it is a write and then a read. So typically, the write data specifies what is to be read, for example, a memory address or a register number, and then that value is read. So here we can see how this works. We do the first operation as normal through here, and then where we would normally generate a stop condition, we generate another start condition. This is called a repeated start. Then we do the next operation just as we would before, and in that case, if this is the last operation, we generate a stop condition. Now, the significance of this feature is its slightly more efficient use of the bus by having just a single transaction. But perhaps the most significant thing is it acts as a single atomic operation. No intervening bus transactions can occur between these two operations. And we'll look at that in one of the prompts at the end of the lesson. So this is the last slide in the set of features and procedures. So we have here 10-bit addresses, which is obviously an extension of the normal 7-bit addresses. 10-bit addresses are not commonly used, but they are possible. As you might expect, an extra byte has been added to the message formats for these extended addresses. It has been designed so that a single bus can have both 7 and 10-bit addresses. And you might wonder, how can you do this? Well, what has been done is that 7-bit addresses with values that look like this, 4 ones and a 0, followed by 2 other bits, are reserved. They can't be used for any 7-bit address device. And so the way this works is when the master wants to talk to a 10-bit address, it sends first a 7-bit address of this form. This here is the reserve pattern, so no 7-bit device will match this. And in this byte, these last 2 bits represent the first 2 bits of the 10-bit address. So if any 10-bit devices match this, they will send an ACK. Might be more than one because we're only talking about the first 2 bits. And open drain allows multiple devices to send an ACK. Then the master sends the second byte, and 8 bits here plus 2 bits here, that's your 10 bits. Now there should be no more than one device who recognizes that address as its own, and if so, it will send the ACK. This is the important ACK. If this ACK comes through, now the data transfer starts, and this all works the same as before. So that's how 10-bit addresses work. The final feature is called general call address. And what this is that an address value of 0 is also a reserved value, And what it is used to do is to broadcast messages to all slave devices. So all slave devices, if they support this, will recognize that address 0. This is a little bit different than other kinds of messages because the standard talks about the data portion of the message. And the standard has defined some standard procedures for devices to support. One of them is a soft reset of the device. So the idea is that with a single message, the master can tell all the slaves to do a soft reset. Of course, the master doesn't know whether they've received it and whether they've done it, but it is possible. To summarize this lesson, I2C is one of several types of serial communication used with MCUs, some others being SPI and asynchronous serial. I2C is normally used for short distances, typically on a single board or a set of closely connected boards. A major advantage of I2C is needing only 2 signals, meaning 2 MCU pins, to communicate with multiple devices. A major disadvantage of I2C is lower speeds compared to, say, SPI, due to the use of open drain signals. Now, I2C bus activity occurs within a transaction between a master and a slave. Typically, the master is the MCU, and slaves are devices such as sensors, displays, analog to digital converters. Each slave on a bus has a unique I2C address. The master sends the slave address at the start of a transaction. The corresponding slave sends an ACK, and then the data transfer occurs. Here are the prompts for this video lesson. I'll pause here for a few seconds in case you want to pause the video and look at them. On the next set of slides, I'll go through these prompts one by one with my take. With the SHT31-D temperature sensor chip that we use in this course, you can choose the I2C address, 44 or 45, on the fly by connecting a control signal to the adder input on the chip. How could this be used to support more than 2 such sensors on a single I2C bus? Well, my solution isn't very clever, but I think it will work. It requires 1 GPIO output pin for each sensor chip, connected to the adder input pin on the chip. So say you have 4 sensors, A, B, C, and D. If you want to access sensor B, set its adder input via the GPIO, so it uses address 45. Use the GPIOs for the other sensors, so they use address 44. Then you do the I2C transactions using address 45. You will talk to sensor B, and the other sensors will ignore you. Now, this appears to break the rule of every device has to have a unique address, but really, I guess I should say every device that you're actually going to use has to have a unique address. These sensors, when they are set for address 44, are not ever going to be used with that address. Why might the master on an MCU stretch the clock? Well, I can think of 2, and to be honest, I got these based on reading the MCU reference manual. And there might be other scenarios, but these are the 2 I'm aware of. So in the case of a write, if the MCU software is not providing data to the I2C peripheral fast enough in a transaction, then the I2C peripheral is forced to stretch the clock until it gets more data. What else is it going to do? In the case of the read, if the MCU software is not fetching data from the I2C peripheral fast enough, the I2C peripheral will have no room to store more input data, and it's forced to stretch the clock to stop the slave sending data. Now, in these cases, for instance, in the driver we develop, the I2C peripheral would be interrupting or sending interrupts to the MCU trying to tell it there's data for you to read, or I need more data. But of course, you can't force the MCU software to do that. So that's when this would occur. Suppose you have two sensors on an I2C bus and you cannot achieve a fast enough sample rate due to the bus. Describe possible solutions. Well, this is a pretty open question. My first response is to improve your code. There might be bugs in it or something. It might just be doing something stupid that is limiting the throughput. It's hard to say. The next two are a little bit more clear. One is to go to a higher bus speed. So if all the devices on the bus support, say, 400 kilobits, but you're only running at 100 kilobits, well, you can get quite a speed increase there. Another possibility is to put the devices on separate I2C buses so you can communicate with them in parallel. That obviously should more or less double the throughput. Assume you have an I2C memory device, and to read a memory location, you first do an I2C write to indicate which location you want, and then you do an I2C read to get the value of that location. In the case of multi-master, what is the danger if you do not use the combined format to do the write plus read? Well, the scenario that would cause a problem is master 1 writes that address value, and now it wants to read the value, but master 2 sneaks in and gets the bus and writes a different address value. Then master 1 finally does its read, and it gets the value for the wrong address. So this interleaved use of the bus is what is the danger. Now with combined formats, the write and the read operation is done in a single atomic bus operation. And so master 2 could not sneak in between the write and the read of master 1. Describe limitations of using an I2C software reset command to fix a stuck device. And I think I briefly mentioned the ability for a master to send a reset command to a slave telling it, restart yourself. And this might be done in response to some kind of problems on the bus. Well, I thought there were two. I can really only come up with one now. And that is the stuck device might be holding down the SDA or SCL bus signals, in which case you can't do anything on the bus. Or it might have a problem in its I2C interface, in which case communication to it is impossible. So the main problem is the device has to be somewhat working to even send a software reset to it. Suppose you had two slaves on a bus with identical addresses, and the master tried to do a read of 1 byte using that address. The one slave tried to respond with a value of hex FA, and the other slave tried to respond with a value of hex 0F. Would the transaction work? And if so, what value would the master receive? Well, the answer to this depends on the fact that with open drain, a low signal takes precedence over a high signal. So if one device is sending low and the other device is sending high, and keep in mind sending high means you just leave the signal alone, then the overall result is a low signal. So the transaction would work. Both slaves would ACK the address, which is a low, and the master would read that ACK with no problem. With regard to data, one slave sends FA, which in binary is this, and the other slave sends hex 0F, which in binary is this. And if you take these two binary strings and consider them being sent bit by bit, and keeping in mind that if there's a 0 and a 1, the net result will be a 0, then when you combine them, you will get this value, which in hex is 0A. And that's what the master would receive. And keep in mind that the master would not be aware that two slave devices responded, and the slaves would not really be aware that they were responding in parallel with each other. Well, this was a long lesson. I hope it was useful for you, and thanks for watching.